I'm just going to run through the solution to FEEG1003 workbook question 10.4 from the 2016-17 version. It's a fairly simple question, but it's good in the way that it asks you to derive a fairly simple formula. We're given the basic expression here already, so the difference in the momentum force is equal to the net pressure force. And actually this question is quite useful because you can work backwards from the answer to make sure that you derive the correct parameters and balance the units and dimensions of each term as well. So we have a duct. It's a two-dimensional problem, so we have a unit thickness, we don't have a cross-sectional area. We have fluid coming in from the top at some angle, and then fluid exiting here. And in the diagram in the workbook, which I've replicated on the board, we've got x and y axes, so we've got our sign convention. We've got a control volume drawn on, dashed in blue here, with height h, and then we have, we're assuming some positive gauge pressure inside that control volume, PC, and then presumably some sort of atmospheric or exit pressure, which is lower, P0 outside. Okay, the first thing we're given the basic equation. Now usually we'd express momentum as the mass flow. So every time you see a dot over a letter, it's a rate term. So this mass flow would be in kilograms. So kilograms per mass per unit time, so per second, times velocity. Now that mass flow, kilograms per second, is also equal to rho q. So it's exactly the same units and dimensions. So q, as we know, equals u times a, so the velocity times the cross-sectional area. So then we have an expression rho, sorry, that should really be a u, shouldn't it? I've got my civil engineering brain working today. So we use v for velocity, because velocity begins with a v, but convention states that for everyone else, velocity begins with a u. So rho q, which is ua, times u again. Okay, but we don't have a, all we have is the unit thickness, this value t. So we're going to work it out per, so in two dimensions basically, so per unit depth or width or whatever it might be into the board. So then we have rho t times u, and then times this other u term. So that's what we have coming out. Very easy to do. It's all positive. It's all in the x direction. The x momentum in is slightly different. You can see that it's the component we're looking for, so we're working it out in the x direction. So it's got a negative sign. There's the magnitude of the velocity coming in. We take the cosine of the angle equal to the adjacent over the hypotenuse, and it's a negative. So in terms of x momentum out, we have rho t u oh. So rho tu minus u cos theta. And then finally the pressure force is equal to the differential pressure, so PC minus P0 times the height h. Now effectively what we can do, we can just rearrange that expression to give you the answer in the workbook. So if we take PC over this side, or the differential pressure, sorry, PC minus P0, we can take the PTUs out. So, sorry, rho. And we can take the H across and divide through. Okay, so that's an intermediate step. And then we take the V's out of here, two negatives make a plus. We end up with the PC minus P0 equals rho T U squared over H 1 plus cos theta, which is the answer in the book. And this equation you can then apply to the next question in this section concerning, I think, the outlet velocity and the mass flow rate to keep a hovercraft. So basically a platform with some mass hovering above the ground. So you can rearrange this equation. I think in the question you can rearrange it for V, for the velocity, or U, whichever you prefer. To work out the velocity in that after you've done a basic force balance. So that's the basic answer to the question. Again, study the diagram carefully. You're given the equation, so it's a case of just working out the expressions for each, making sure that they're dimensionally equal. Again, this is the general form in terms of force that we'd use. So the mass flow rate kilograms per second times the velocity. Often that is just, if we're working out force in, say, pipe bend, something like that, you generally write force equals rho Q times velocity. If we know the fluid, we know the density, you can expand this out as well. So you can expand Q out, so we end up with rho A U squared. Okay, Q equals U times A, and that has units of meters cubed per second. Okay, so basic introduction to that question to conservation of momentum.